Here again is Dama. Thank you for joining me for yet again another edition of my video. If this is your first time you are watching this video, I want to welcome you and thank you so much for joining me. And I can assure you that you are in for a treat today. If you are part of those watching my video, I also want to thank you for your contributions, your continuous support. The likes, the shares, and the positive comments are extremely helpful. The reason I titled this work as Cantilever is simply because it is one of the classical advanced questions in physics laboratory exams. What is a cantilever? A cantilever is the projection of a beam that has one end fixed and the other end horizontal projection freely standing in space as seen below. We are going to use a cantilever to compute the Young modulus of this meter rule. The Young modulus of a meter rule is nothing but the property of the material that tells us how easily it can be stretched or deformed when subjected to a force. It is the mechanical properties of the material. We need to know it so as to know the best kind of materials that can be used for reinforcement in our laboratories. Now, this is a setup for the Young modulus experiment using a cantilever. In this procedure, it is a simple procedure in which a 100 centimeter rule is being fixed at a specified position. The specified position we are starting here is 20 centimeters is left vibrating freely on a space, while the remaining 80 centimeters is fixed to the bench. We are going to take the depression caused by this mass attached to the fixed end of the meter rule. It's a mass of 200 grams, which causes a depression. At 20 centimeters, we have a slight depression in which we measure it with our ruler and label it Y. Now, we extend it with another 10 centimeters in which we have 30 centimeters vibrating as a cantilever here. This is 30 centimeters. And the depression increases Y here, which was measured again with a meter rule. Subsequently again, we extend it to 40 centimeters as seen here. And with 40 centimeters, the depression increases Y. We do it for the remaining 3 values to get 6 complete values for this procedure. Now, this is the result we got here on the board. The result shows that X is in meters. This is the vibrating end of the cantilever. We have 0.2, 0.3, 0.4 up to 0.7 meters. The depression we obtained against each vibrating end of the cantilever are these 3, 4, 8, 45, but they are all in meters, whereby a standard form is introduced, 10 raised to the minus 3 as our Y. Now, some people would be wondering, how do we get this column? Simply, from the equation of this cantilever, we have Y is equal to 4 mg x raised to the power 3 all over E B d raised to the power 3. Now, we can see here that m is the mass attached to the end, which is 200 grams or 0.2 kilogram. Our g, acceleration due to gravity, is 9.81 meters per second square. B is the breadth. That is the breadth of our meter rule. The breadth of our meter rule is gotten, and the value is 29 millimeters, which is 29 times 10 raised to the power minus 3 meters. While D is nothing but the thickness of the meter rule. And the thickness was measured using a micrometer screw gauge as seen here. And we can see the main scale of the micrometer screw gauge is 5.5, while we record the thimble scale. The thimble scale coincides at 29 reading, which is 0.29 millimeters. When we add this thing, we'll get 5.89 millimeters as our thickness for this meter rule. Now, in physics, all equations must be transformed to straight line. Introducing straight line equation, y is equal to mx plus c, juxtaposing this one with the equation of our graph, we have this one here. And if we can see here, the intercept here is 0 for this equation 2. So therefore, we're expected to plot a graph that passes through the origin upon taking our results with all carefulness. Therefore, a graph of y against x raised to the power 3 will give us 4 mg all over e bd to the power of 3. This one here is our slope. So our slope gives us 4 mg over e bd to the power of 3. Marking e subject to a formula or Young modulus, we have e is 4 mg, in which we have our slope multiplied by b d to the power of 3. And upon slotting, we'll get the value of our slope. Now, let's see our graph, and it says what it. So now, this is the graph of y versus x raised to power 3 in meter to the power of 3, and these are y is in meters. If we want to choose the scale, we can see from the table we obtained on the y-axis times 10 raised to power of minus 3 meters, we have the maximum value of 45. And if we have 24 boxes, if we must put these 45 units to meet up to 3/4 of this graph, it ensures that 1 centimeter will represent 2 units. So therefore, if this one is 4, we have 8, we have 12, we have 16, we have 20, we have 24, we have 28, we have 32, we have 36, we have 40, we have 44, and we have 48. On the x-axis, which is x raised to power 3 times 10 raised to power minus 2 meter to the power of 3, we have 20 boxes here, and the maximum on the x-axis is 34. So therefore, for us to have a complete coverage that will cover 3/4 of this graph, we also equally have 1 centimeter to represent 2 units. That means on both axes. Now we have here as 4, 8, 12, 16, 20, 24, 28, 32, 36, and we have 40. So now, let us start plotting our points. The first value on the y-axis is 3. If this is 2, it means 3 is here. And if we have 3 on our y-axis, on our x-axis, the first value is 0.8. This is 2, this is 1, and here we have 0.8. So therefore, we have our first points as here. The second value, here we have points, we have 4 at the y-axis, and we have 2.7 on the x-axis. This is 2, this is 2.7. So our next point is going to be here. The third point, we have y at 8. This is 8 for y. And the x-axis, we have 6.4. This is 6. 6.4 is around this side here. So the next point, we have 15. This is 12, this is 14. 15 is here. And our x-axis, we have 12.5. This is 14. This is 13. And 12.5 will fall in this range here. And our next value, we have 28 on the y-axis, and we have 21.6 here. This is 20, 21.6 will be around this side here. The next point, we have 45. This is 44. This is 45 here. And our x-axis, we have 34. This is 32, 33, 34.3, which will fall in here. So now, let us draw our line of best fit. Our line of best fit will pass through the origin if our points are correct, which we see is almost at the origin, with two points outside here and the other one here. So now we are going to take our slope. If we must take our slope, it should be a large right angle triangle. So therefore, we take it from this side here. If we take our slope from this side here, we have this side here. So this slope will be taken here. This is the slope m, whereby we have this value here as our y2, which is equal to, this is 40, this is 42, and our y1 is 4. Our x2, we have 32, our x1, this is 2, this is 3, x1 is 3. Yes. We can see here that our slope, changing y by changing x raised to power 3, is given by 42 minus 4 all over 32 minus 3. This one, 10 raised to power minus 3, 10 raised to power minus 2. We have here 38 all over 29. This one here times 10 raised to power minus 1. If we punch our calculator, we will have 38 divided by 29, we have 0.1310 as our slope. So therefore, upon inserting in this equation, we have E is equal to 4 times 0.2 times 9.81 all over slope, which is 0.131 times our B. Our B, we got it as 29 times 10 raised to the power minus 3 times our D. Our D, which is the thickness, is 5.89 times 10 raised to the power minus 3 all to the power of minus 3. So therefore, we get the value of our Young modulus, compressing this one, to be the value of a Young modulus is 10.197 times 10 raised to the power 10 Newton per meter squared. So therefore, this value of Young modulus is showing us the mechanical property of this wood, which we used it in making our meter rule. So this is a classical solution to this kind of problems on Young modulus, which we always encounter in physics laboratory exams. Thank you for watching. Have a nice day. Bye-bye.